Chocolate, the staple gift of Valentine's Day. Today we're going to use it to calculate the speed of light with a few common household items. So, we have our microwave, we have our chocolate, we've got a ruler, and we've got a calculator. Let's put the chocolate in the microwave. To demonstrate the shape of waves, we're using Arbor Scientific's standing wave kit. So imagine that this is the microwave as it travels through the oven. The generated microwave set up a standing wave pattern where the overlapping reflected waves meet oncoming waves. We are only able to demonstrate the one wave here, but picture this bouncing back on itself, and at some point the waves will overlap. At each of the two melted areas, the waves add constructively, with one melted area formed by the wave crests from one direction adding to wave crests from the opposite direction. And the next melted area is formed when wave troughs are adding together. And between those two areas, waves are crossing out of phase with crests and troughs, canceling each other out. Since one melted area is produced by wave crests adding followed by the corresponding wave troughs adding, and we know that this only forms half of the wavelength, you have to multiply by 2 to get the full wavelength in this demonstration. And voila! Here's what happened to the chocolate in the microwave. As you can see, there are multiple melted spots. This is why we covered the whole plate with chocolate to make sure that we get more than one melted pair. With a ruler, measure between corresponding melted spots. Each pair of melted spots are just over 6 centimeters apart, which we estimated at about 6.1 centimeters. We found this to be fairly consistent with all of our pairs. As we mentioned, this is only half of the wavelength, so we'll double it during the calculation. And finally, we can calculate the speed of light, which equals the wavelength times the frequency. Our microwave's frequency is 2.45 gigahertz, which comes out to 2,450,000,000 hertz. We calculated the full wavelength by multiplying our measurement by 2, which comes out to 12.2 centimeters for the full wavelength. Next, we convert centimeters to meters for our speed of light calculation, which gives us 0.122 meters times the 2,450,000,000 hertz, and that equals 298,900,000 meters per second. The actual speed of light is 299,792,458 meters per second. So it's not exact, but this is very close for doing this experiment with a home appliance right in your classroom, and it's a great way to demonstrate the speed of light with everyday things. This is Keith Bourne with Arbor Scientific, wishing you a happy Valentine's Day and a day full of fun and educational physics exploration.